so we're going to look at a simple rational function. Let's say f of x is 2 minus x over x minus 3. And I want to, and you're going to see one of these on your first test. So you're going to see a question from test 2 on test 3. In fact, I'm going to put a difference quotient on test 3 as extra credit, right? So I'll let you score up to 110 on test 3 as well. So I want to start talking about a couple of things. First of all, what about domain?
X theta equal 3.
Beautiful. And what about range? This is hard to answer. Who knows what y values are excluded from this particular function? We know the x values that should be excluded. Which y values will be excluded? So and this is a main point here, is that if we could figure out the inverse, so if this turns out to be 1-to-1, there's an inverse function. If we could find the inverse function, that we do that by switching domain and range. So if I can find the domain of the inverse function, I end up finding the range of the original function. And this one is y does not equal -1. Can anybody see why from the original function, why this height is excluded from the graph?
So because of the asymptote?
Exactly. So sometimes a horizontal asymptote can be crossed in the short run. And in that case, we wouldn't get that same result. But we would still be looking at the inverse function to find that domain to be able to talk about the range of the original. Okay? So, nice, Ryan. What is the vertical asymptote?
X equals 3.
Beautiful. What is the horizontal asymptote? Oh, we already got it, right? Y equals -1. From the mother functions, what's the mother function of the numerator? Say again? So from the numerator is -x, right? From the denominator is just x, yes? So that's like -1. Here's my horizontal asymptote. What are the what's the x-intercept? Or what's the y-intercept? That's easier, right?
-2.
Nice, -2. So 0, -2/3. Remember, to find the y-intercept, you plug in x is 0. How do you find the x-intercept?
Function equals to
Set the numerator equal to 0. Yes, the function too. And then when you cross multiply, the denominator goes away anyway. So 2, 0. Is everybody okay here? So I want to try and put the graph down. And remember, when you're doing this on the test, you're going to put it on the calculator. And so that you've got this kind of safety net, right? But I have an x-intercept at 2, 0. I have a vertical asymptote at 3. I have a horizontal asymptote at 1. I've got the points, so I have my 2, 0, and I have my 0, -2/3, right? And then I'm going to also ask for short run. What's the short run at x equals 3? Who's got that? Oh my God, there's only 15 students here today.
It doesn't make sense because it would be -1/0.
Oh yes, but so that's the key about short run behavior. And this is my method, okay? You can't plug it into x minus 3, right? So you plug it in where you can. So 2 minus 3 over x minus 3 is -1 over x minus 3. So you can see it should be looking like a -1 over x. And so here it is. There's that piece, and here's that piece. Which makes sense because it has to go through those points in that upper left coordinate, right? Upper left quadrant. I missed, but I'm close enough. I'll try and get them. Close enough, right? Is that making sense? It should look like, in general, a -1 over x curve. Right? It's going to look like one of those four. 1, 2, 3, 4. 1 over x. -1 over x. 1 over x squared. Or -1 over x squared. It's going to look like one of those four. Of course, x cubed looks like x. X to the 5th looks like x. X to the 4th looks like x squared. X to the 10th looks like x squared, right? Even and odd powers look similar. So we don't care about that much detail. We just want to see where the curve is. And of course, you can graph this on your calculator. And then you put all this stuff down to fake me out, to think that you did that first before you got the graph. All right, how do we know this is 1-to-1? How do we know this function is 1-to-1?
It passes a horizontal line
Horizontal
test.
line test. So if I draw a horizontal line anywhere, it's only going to hit one height. That's what we need. We need the heights to be unique. There's no repeated heights. If that's the case, I can create the undoing machine, the inverse machine, right? So by the horizontal line test, f of x seems to be 1-to-1. How do I know for sure? How do I prove that f of x is 1-to-1?
A is f of a is equal to f of b, and a is equal to b.
Nice. Let f of a equal f of b, right? And show a is equal to b. So here we go. So 2 minus a over a minus 3 should equal 2 minus b over b minus 3. Is everybody with me? Anybody need time? Am I going too fast? Well, I don't know about you, but I don't like fractions that much. I'm going to cross multiply. I get 2 minus a times b minus 3 equals 2 minus b, that quantity, times a minus 3. And I don't know about you, but I don't know what those people are talking about in the rooms. Let's break them up. Let's get rid of the associations there, right? Let's distribute things out. So what do I get from this first one? I get 2b. From the second one, I get a -6. From the next, I get a -ab, and then a positive 3a. And that should be equal to 2a minus 6, and then a -ab and a positive 3b. Is everybody with me? Thanks. I can see Elise and Ryan Cindy's got the thumbs up going. Thank you. Thank you, Brian. Daria, nice. Wilder, nice. So I see some things that match up that are going to go away. The -6 goes away, and the negative AB goes away. So I've got 2B plus 3A is equal to 2A plus 3B. And then I want to move things and minimize the number of negatives I have. So meaning I'm going to move the A terms to the left and the B terms to the right. I would like things to end up positive if I can. So what do I get? I get A equals B. That's it. That's what I wanted. So f of x is 1 to 1. This is going to be an easy first question on the test. Easy. Now that I know the function is 1 to 1, what do I know? Once I know a function is 1 to 1, what do I know about it?
As an inverse.
Right. So once I know f is 1 to 1, f inverse exists. I can now find the inverse function. Sometimes it's not easy to find the inverse function. And you'll see sometimes the inverse functions are going to give us a little bit of grief in Calc 1. Sometimes these inverse functions will give us some grief in Calc 1. But we need them. We need to be able to drive forward and backward. I told you, right, about my license, the test when I was getting my license and I failed it. The instructor said, go ahead and back up. So I just stayed there, and then he failed me. Rotten bastard. So since we know the function is 1 to 1, we can find the inverse, and that's our next piece here, right? Pretty long first question on the next test. You know, it's going to take 5 pages to write it out, but what else you got to do, right? So we know that f of x is what? 2 minus x over x minus 3. And so we rename that as y, right? Because we want to think of x's and y's as simple objects. And again, we don't really like this fraction piece here, so we're going to cross multiply. And we don't like this association. Why are they excluding y here? Let's get y involved, so we multiply. xy minus 3y equals 2 minus x. Don't let me go too fast here. I feel like, did I have coffee today? I feel like some kind of caffeine just kicked in. We okay? I would like to solve for x, so I want to get all of my x terms on one side, minimizing the number of negative signs. Now, it's not wrong for me to do it any way I want, but I will have to simplify a little bit if I have extra negative signs. So it looks like on this one, if I move my x terms left and my y term right, I get a pretty nice version of, right, I get no negative signs. That's ultimate. 1 would be fine. 2 is pretty normal. If you get 3, you could have done it another way. If you get 4, you could have done it another way. Okay. So now it begins with an F, ends with a Sidney Poitier. What am I doing here on the left? Begins with an F, ends with Tom Cruise. Factor, yes. Begins with an F, ends with an actor. So I get x times y plus 1 equals 3y plus 2. What, I don't get any groans for that bad joke?
It was pretty good.
So I get x equals 3y plus 2 all over y plus 1. Once I get solved for x, I want to switch my x and y. right? This is the whole concept of this inverse function. So I get y equals 3x plus 2 over x plus 1, and that's what I'm going to call my inverse. In fact, I like to call it G, because I don't, what up G? I just like to say what up G instead of what up F inverse. It's too much. So I've got my inverse machine, I've got my original function, I've got my inverse. Look at the domain of the inverse. The domain of the inverse is x can't be negative 1. That happens to be the range of the original function. Y can't be negative 1. So I had talked about it's hard to find the range of things, but if you can find the inverse function, it's easy to find the domain of that, and then you end up finding the range of the original function. Because remember, x and y are switching. Domain and range are switching. Okay, so we've got a function. We've got the inverse. We want to see if we can just double check it with something simple. Right? So we're going to pick something in the domain. What's my function? 2 minus x over x minus 3. So I want to pick something nice and simple in the domain of f. See what comes out of it. Put that output into G and see if I get back to the beginning again. Right? So I know f of x is 2 minus x over x minus 3. And f inverse, which I'm calling G, because I'm lazy, is 3x plus 2 over x plus 1. So who's got a nice domain value for me for f? Who's got an x value in the domain of f? Who can give me one? Anything but 3, right? So whatever you want, you just give me one.
1.
Sure, 1. I like 1. I love words that have that, that double spelling, so you can always make jokes. I won the competition. How many teams? 1. So 2 minus 1 over 1 minus 3 is 1 over negative 2, so negative 1/2. So we're going to take that output, right? We agree here, negative 1/2? We're going to take that output and put it into G and see what happens, right? So G of negative 1. So 3 times the negative 1, negative 1/2 plus 2 all over negative 1/2 plus 1. So minus 3/2 plus 2 over minus 1/2 plus 1. Right? And I'm doing arithmetic here, so you do it the way you want to. I'll do it the way I want to, right? I personally would go with the 2, right? Multiply by 2 over 2. So I get negative 3 plus 4 over negative 1 plus 2. So I get 1 over 1, which is 1. Hey, what do you know? I got back to where I started. And this is the key. When I compose inverse functions together, everything falls apart. The multiplication and the division cancel. The addition and the subtraction cancel, etc., etc. Everything will fall apart, and I'll get left with what I started. Right? What I started with is what will come out. The wrinkly dollar bill into the soda machine. Right? Now, it's not good enough for us to do this with a single piece of domain. In fact, it's not even good enough for me to do it with an infinite number of pieces of the domain, because it will take me forever. I'll be dead long before I finish the problem, right? So I want to be able to do it in general. And how do we do it in general? We show that the composition of the functions, f composed of g and g composed of f, give us the result of what we started with, which was x, right? Show g composed of f of x equals f composed of g of x equals x. Everything should fall apart except for whatever you put in. And you can clearly see my input is x. That's what I'm putting in. That's what I should get out when I compose a function in its inverse. How are we doing here? Who is not going to get this first question right on test 3? You're all going to get this question right. 4, 8, 12, 15 of you out of 24. What happened? You're dropping off like the Willy Wonka kids. One of them fell in the river. One of them turned into a blueberry. Do you even know what I'm talking about? I just feel like I'm so old sometimes. Like, why would anyone know that movie but me? But okay, so let's do at least one of these. Let's do G composed of F. So G of F of X is G is this function 3 times x plus 2 over x plus 1. And inside of that, I'm putting the function f. And this is what I used to do as a student. I would put the letter f in there because I was so confused. I just wanted to first write the first function and then put something quick in so I didn't have to, right? So I'm putting that function f inside. But I know what that function f is, right? That function f is the 2 minus x over x minus 3. Cindy, there's one of those things that I had to do to get myself to understand it, to know what was really going on, right? Just to kind of put a quick placeholder in there so I could think a little bit. Now, what's my little trick here? Well, I have fractions within fractions. So this is called a complex fraction. I'm going to clear those interior denominators, looking for a common denominator, right, over itself. And that's clearly x minus 3 over itself. And let me make that in red. How's everybody? We okay here? Nice Wilder. Wilder's got some new energy. All right, I want to distribute, and I want to try and do this slowly. Okay, so I'm going to try and keep my colors intact here. I have 3 times f plus 2, and all of those I'm going to distribute this red x minus 3. Right, and so inside of that first one I have the 2 minus x over x minus 3. So I'm hoping you can see from one line to the next, you can see the black is intact, the green is intact, the red is intact, and then you can see what's actually happening on the next line, right? So I've got, my 2 minus x over x minus 3, multiplying that by the x minus 3, and then plus 1, times that x minus 3. Does everybody see what's going on there?
Yes.
So I'm trying to go slow, I'm trying to do baby steps. There's plenty of time on the test. No time to sit there. You got to be writing the whole time, right? Shards of pencil are shooting up as you're writing, and your eraser's down to the nub, and you switch out the pencils real quick, and you start again. It's just like... All right, I can see things that cancel. The x minus 3's will cancel here and here. That's nice. And now I'm rewriting. I'm not trying to do anything while I rewrite. I got 3 times 2 minus x plus 2 times x minus 3 all over 2 minus x plus x minus 3, right? Multiplying by 1, that one I think I can handle. So now I'm distributing upstairs. And then trying to cancel things. So it looks like the 6's will go away upstairs and the x's downstairs. So I've got negative x over negative 1, and there it is, x. Yes. So I know the functions are inverse now. Well, I have to do the other composition. There are times when one composition will deliver x and one won't. Not the one I'm giving you. Okay, the one I'm giving you will be I'm giving you something that is one-to-one. And we proved it's one-to-one already, right? So it's like overkill here, but it's all the kind of pieces of understanding functions that I want you to know for calc, right? All right, cool. So our first question is coming from 3132. Our second question on the test is going to come from 3536. Okay, but we have some little pieces that we have to clear up before that. So in 3334, our first question is coming from 51, right? Our next test is chapter 5, chapter 6. So I got one question from 5152. The second question is going to come from 5556. So we're learning that Friday. Okay. And we'll see the main problem that you have to be able to solve. Okay. But there's some, I guess, prelim stuff. There's some understanding stuff that has to come, and that's today's lecture from 5.3 on exponential functions and 5.4 on logarithmic functions. Okay, so it's a little bit boring, so I'm sorry. I did already record it with the other class, so if you fall asleep, no big deal. It could happen. So what we're talking about today, and I should be able to finish them both, is 5.3 is my exponential functions. And this is important stuff for like the bio and chem and all of that. It's like how things grow, or how you date a fossil kind of thing, right? Half-life, all of this kind of stuff, right? So population grows exponentially, money grows exponentially, right? Not my money, but other people's money, I guess. So finance, nature, these exponential functions and log functions come into play quite a bit. Like the logarithmic functions, I love the applications of earthquakes and decibels, noise, how coffee cools. Like if you pour yourself a cup of coffee and then keep checking the temperature, that all of that is with exponentials and logs and that type of thing. So it's a lot of interesting applications. But anyway, so what does an exponential function look like? So we'll say that f of x equals c times a to the x plus b is an exponential function if a, which is the base. So think of 2 to the x, 2 to the 1, 2 to the second, 2 to the third, 2 to the fourth, right? I need something to be growing really quick, right? 2 to 4 to 8 to 16 to 32, right? So if a, the base, and it's all about the base, right? We know this. It's all about the base, If a does not equal 0, does not equal 1 and is not negative. So a is the base of the function. It's going to be fixed. Okay. C is called the initial value. And B is the horizontal asymptote. In general, I'm going to see an exponential function with my same old mother function 1 by 1 box, right? This 1 by 1 box. I'm going to get this exponential function from here. I missed it. It's not easy to do. So I'm going to get that exponential function there and my asymptote there. So there's y equals b. There's the point 0, comma c. And there is my y equals c a to the x plus b. So I get a couple of things just from this picture. And of course, anytime I give you an exponential function, put it in your damn calculator, please. Right? Put it in the calculator and then make me think you know what you're doing on the paper, right? And I'm telling you, if you practice, you will, right? So what can you tell me here about domain? What's my domain here?
Everything.
Yep. So all reals or minus infinity to infinity, right? And what about my range?
0, infinity.
Nice. And 0 is not included, right? And so when I give you a new function, we're going to move this kind of picture around, right? Like when we had a rational function, we had a horizontal vertical asymptote, and we moved that around, and that became the new origin. And now what we're going to do is move this horizontal asymptote and that box, right? We're going to be moving that around, just like we did, right, with the other functions. This is the range. So you certainly can see me doing like some kind of transformation of the function, right? But let me pick a base. Let me pick a nice base, and let b be 0 and let c be 1, right? So is everyone's okay here? Yeah. So like y equals 2 to the x, right? What does that look like? I should go back. Sorry, let me go back. I should explain some of this stuff here, I guess. This stuff. Why is that stuff important? Okay, and you don't have to write it, you can just listen. Well, if it's y equals 1 to the x as my function, that's boring. 1 to the 7th, 1 to the 0, 1 to the -2, it's always 1. So this thing is not growing at all, right? I want my exponential function growing. So if I have a base of 1, it doesn't grow at all. If I have a base of 0, it's trouble. So this one is just plain old boring, right? It's not an exponential. If I had something like y equals 0 to the x, for any positive x, this is pretty boring. 0 to the 10th is 0 times 0 times 0, 10 times 0, right? 0 to the 0 is trouble, okay? And you'll learn this in Calc 1, something called an indeterminate form. Sometimes 0 to the 0 is 1, sometimes it isn't. So, and that's a weird thought, but it's a big piece of Calc 1. So, but the real issue is, so 0 to the 0, we don't really know what it is yet. That's a big question mark. You're going to have this answered next semester, okay? But 0 to the negative 1/2 is trouble, right? Because what is that? That's 1 over square root of 0. It's trouble. Can't take it, right? Any negative power is going to put that 0 downstairs, right? And then I'm in trouble, right? Elise, bless you. Was that a sneeze?
Yeah.
You know which
I thought I was muted for a second. I was like, uh-oh.
No, I didn't hear it. I just saw it. What? Do you know which way a sneeze points?
Down.
At you.
Oh.
So these are trouble if my base is there. And of course, if the base is negative, like y equals negative 1 to the x. Well, when I let x be 1/2, right, I've got a square root of negative 1, and that's complex. And we want to stick with real numbers, no complex numbers. So I can't have my base be negative, I can't have it be 0, I can't have it be 1. And more importantly, if 0 is less than a is less than 1, then f of x decreases. So that would be like half-life, how much radiation is left, kind of thing, right? And if a is bigger than 1, then f of x increases. So money in the bank, money on your credit card, charges on your credit card, population of bacteria, humans, etc. Right? Okay. So we're going to look at this simple function. Of course, what am I going to do? I'm going to put it in the calculator, right? And all right, clearly I can get some points on this very easily. What's the point right here? What's the x value there?
Zero.
Yeah, 0. So the x value is 0, so 2 to the 0 is 1, right? And so, of course, you can see it's a 1 times 2 to the x. So you can see that initial value there, right? And I'm seeing my horizontal asymptote, and I'm seeing my 1 by 1 box. So we want to look at what happens if I have y equals 3 times x minus 1, 3 times 2 to the x minus 1 all plus 1, right? So now all of a sudden you can see I've brought in some transformations here. Well, let's see if we can handle the scale factor first, that multiplier out front. It says 3 times, right? So when I put in, so I want to be able to graph y equals 3 times 2 to the x, right? Because I'm trying to think of the mother function as 2 to the x, daughter function 3 times 2 to the x, granddaughter 3 times 2 to the x minus 1, and great-granddaughter all plus 1, right? I'm trying to get all the way, take little baby, that's funny, baby steps. Mother, daughter, granddaughter. I'm trying to take baby steps to get to each transformation here. So what's this one going to do? Well, I had my original 1 by 1 box, but it's going to change now, right? What's the height of the box going to be now? Yep, 3. So you can see my box has shifted here, right? And now my exponential is a lot steeper, right? Remember, that's what that multiplier does. It just It stretches everything out if it's bigger than 1, and it compresses it if it's less than 1. So there's my 3 times 2 to the x. Hasn't changed my domain, right? Or my range. Right, I still have that same horizontal asymptote. But let's go to the granddaughter now, right? We've got y equals 3 to the 3 times 2 to the x minus 1. What is that doing to the graph? Shifting it over 1 to the right. Remember, x's behave inversely. So this says my new input is x minus 1, right? So what makes that 0 is 1, so I'm shifting that everything to the right 1. And then what happens next? Where's everything going to move now? Hello? Anybody there? Up 1. So now all of a sudden my domain, right? This domain is still everything, but the range is 1 to infinity. So I'm going to just be looking at how I'm transforming a particular function and then, right, move everything. Look at it, it's a family tree. So there's one more thing to do in this section, and that is to talk about how to solve simple exponential equations. So I might have something like 5 to the 2x minus 1 equals 25. And the whole idea here is that I notice, so first of all, what's my base here on the left, do you think?
5.
Yep. Is y equal 5 to the x 1 to 1?
Yeah.
Yep. Passes the horizontal line test, right? So if I can write both sides base 5, and I can, because this other side here is 5 squared, I can see that I've got y values here. You with me?
Yes.
I've got y values. I've got 5 to the x values, right? So I've got exponentials. I've got exponential functions here that are 1 to 1. I already know they're 1 to 1, okay, because of the horizontal line test. So that means since my outputs are equal, what has to be true about the inputs? It's a 1 to 1 function, and I've got 2 outputs equal to each other, 2 y values equal to each other. What has to happen?
Powers have to be
that's right. The inputs have to be equal to each other, right? So because I know I'm dealing with a 1 to 1 function, I automatically, it's like I can ignore the base, right? Something else is really happening that I'll show you a little bit, but so now I can solve this. So 2x equals what? 3. So x is 3/2. When you're doing these equations, always check your answer. There will be some equations that we do in 5, 6, that will lead to extraneous answers. Answers that work out because of the algebra, but when you plug them back in, they don't make sense. Right? Things will work out, but when you put them back, when you go back to the beginning, you realize, nope, that's not right. So we want to make sure we're checking answers when we do things like this. So solving simple exponential equation, we just have to write both sides same base and then set the exponents equal to each other. Is everybody okay there? Anybody want to see another one? Anybody want to see another one of those? I'm not looking at you right now, so I can't tell if you're.
So when the bases are the same is when we make sure that the exponents are equal.
Exactly. Okay. If the overall value is equal, those are y values, then we can go say, well, if it's 1 to 1, then we know that whatever was the exponents had to be equal as well. And it's definitely a little bit funky. So, but let me just bring up one more problem. I'm just going to open one from the homework. So this one's kind of annoying, isn't it? And I'm sorry if this stuff is too easy for you. But run with it. If it's too easy, good. So what is the answer for x?
6.
Yeah, I'm sorry. It's so annoying, isn't it? Right? So there's a 4x plus 1. 125 is 5 cubed, right? Let's do one more here. There we go. So 64 to the negative x plus 52 equals 128x. Actually, let me not do that one. Let me do this next one. No, that's good. Negative x plus 52, 128x. So these are base 2. Am I right?
Yeah.
Yeah, base 2, right? So I want both of these base 2. So 2 to the 6th is 64, am I right? Say again. 2, 4, 8, 16, 32, 64. Yeah, 6, yes? Ryan, yes? Yeah. And 2 to the 7th is 128. So you can see here, I've got same bases now, both sides. But I'm raising a base to a power to a power. When I'm raising a power to a power, so please excuse my drunk Aunt Sally. When I'm multiplying exponents, when I'm multiplying like bases, I'm sorry, when I'm raising a power to a power, I'm multiplying the exponents, right? So I get 2 to the 6 times negative x plus 52 equals 2 to the 7x. So now I've got it written as the same base. So now I know my exponents are equal. So I know that 6 times negative x plus 52 is equal to 7x. And I'm solving for x, right? what is that? 312? 6 times 52? Yeah. So it looks like I have 13x equals 312. So I get x is 24. Is everybody okay? Nice. Cool. Let me move on. There's one little piece I didn't do yet in that section, but I'm going to do it first thing here as I move on to my next section, which is logarithmic functions. And I know it's horribly boring today. So the very first thing I have to do when I'm talking about logarithmic functions is I have to compare them to their brother, sister, whatever you want to say, their inverse function, which is the exponential. So we did this once already, but we're going to graph y equals 2 to the x, right? And so I want to just pick some values here for x and y, and typically I try and do something symmetrical about 0. So minus 2, minus 1, 0, 1, 2. So I'm going to graph the 2 to the x. I already know when I put in x as 0, I get 1, right? So I definitely get the 0.01. When I plug in 1, I get 2 to the 1, which is 2. So I get the 0.12. Is everybody with me? When I plug in minus 1, I get 2 to the minus 1, or 1/2, right? And there's a pretty good version of my, oops, damn it. There's a pretty good version of my exponential function y equals 2 to the x. How are we doing here? We okay? Notice what's happening to the y values, right? Notice what's happening to the y values. What am I doing from one y value to the next?
Adding 2 with you.
Well, yeah, multiplying by the same number, right? Multiplying, right? 2 times 1 is 2. 2 times 2 is 4. 2 times 1/2 is 1, right? So I'm multiplying. Remember what we had from linear? We were adding the same thing. So one of the things they're going to ask you is, you know, if I give you a table, is it linear, is it exponential, or is it neither, right? So you're looking for this multiplying piece to be consistent. And then we're thinking it's exponential, okay? So anyway, if f of x is 2 to the x, f inverse is log base 2 of x. And that log base 2, that little 2 is a subscript, right? It's not multiplying to anything, or it's telling me log base 2. So what's the inverse function of 2 to the x? It's log base 2 of x, okay? And so we already know some values on this table because we're going to just switch our x's and y's, right? So we know that -2, -1, 0, 1, and 2 happen. They were the inputs of 2 to the x, now the outputs of log base 2 of x. And then, of course, we got 1, 2, 4, 1/2, 1/4, right? So if I plot a couple of those, I get 1, 0, I get 2, 1, I get x is 1/2, y is -1, right? And there's my y equals log base 2 of x. And what do you see? Do you see any symmetry? You see that it's symmetrical about that mere y equals x. Remember, y equals x is our magic, because when y equals x, that means x equals y. I'm switching x's and y's. This is the mere for inverse functions, right? Because that's what we're doing. We're switching the inputs and outputs. Now, when I'm looking at log base 2 of x, I'm going, what the hell is that, right? I'm not used to it. Like when I learned to curse in another language, I'd be saying the word out loud in French, but I'd be thinking about what the word actually was in English in my head, right? And so it's the same thing when I'm looking at a log function. I'm not going to think it as a log function right now. Maybe by the end of Calc 1 you can do it, okay? But right now I'm going to translate it into my exponential, right? And so this is the super important thing, is that you know this translation, that this is memorized. If you can't memorize it, you can get a tattoo. I think if that's the real dedication, is if you get a tattoo, that's not cheating, okay? Of course, for us, we can skip the tattoo because it's painful and it costs money, and we can just go on our formula sheet with this translation. So our translation is y equals b to the x is equivalent to log base b of y is equal to x. And I really like to pretend that this is b to the x is like a soda machine, and up in the corner is where you put the coins. So you can see the little coin, right? You can see the little coin slot for the coins there. So I'm trying to emphasize where the input is going, right, for each of these functions. So notice that the input for the log function is a y. What's the output for the log function?
X.
An x. What is the x for the exponential function?
The power.
The power. And this is what we want to be thinking of. A log function is simply generating powers for me, generating exponents. And if I can keep that in my mind, that a log function is just exponents, it becomes really simple. Right now, it's not going to be simple, okay? Next class, it will not be simple. But these are thoughts that I want you to have as you're moving forward. So I would like this translation. We want to really use this translation to almost do everything. Like when you first learn to speak Spanish, like I failed high school Spanish, like I don't know how many times, but anyone speak Spanish here? Not even high school? Cindy, yeah, what does yo no sé mean?
I don't know.
I thought you said you spoke Spanish. I don't know. So, but right when we're first learning a language, we're saying something out loud, but inside of our head. So same thing here. When we were looking at this log function, we're thinking exponential inside. Okay. So for example, if I see something like log base 3 of 9 equals x, I don't know what the hell that thing is saying, right? But I do know the base. What's the base?
3.
Good. What's the exponent?
9.
Nope.
X.
X. And what's the answer?
9.
9. So at this point, we can say, oh, 3 to the x is 3 squared, so x must be 2. Now, and you say to me, well, I don't even need to say, I don't need to do this middle line, and I agree, but eventually you'll see you have to. The questions will be so complicated that you can't just do it in your head like that. For now, yes, you can, right? So this is the big thing, is translate anything written as a log as an exponential, right? And this is really the main lesson in this section. So we're almost done here. Let's look at a couple of problems, okay? So this is in homework 23. So we're up to homework 23 right now, believe it or not. And it looks like we'll probably have somewhere around 40 homeworks at the end. I know you don't want to hear that, but So this one is just saying change it. This one's, I mean, there's nothing to do here, right? I can do 6 to the 4th on my calculator, right? 6 raised to the 4th power is 1296. So there's nothing to do here, but we want to get used to doing this translation, right? So 1296 is 6 to the 4. 1296 is 6 to the 4. How do I rewrite this as my translation? Well, what's the base? This is a double arrow. What's the base here? Come on.
6.
Yep, so log base 6, that's the name of it, right? What's the exponent?
4.
4, that's the answer to a log. The answer to a log problem is an exponent. What was the argument? 1296. Argument, input, etc. when I'm translating, right? So very, very simple. Kind of insulting. Here's one that I'm like looking at this going, what the hell does it say, right? It says log base 6 of 216 is 3. Okay, but that's not my language. I don't know what the hell they're talking about. Log base 6 of 216? Log base 6 of 216 is 3. Translate for me into exponential, which is easy. What's the exponential say? What's the base?
6.
What's the exponent?
3.
6 cubed should be?
216.
That's it. That's how easy it is. And guess what? 6 cubed, 6 raised to the 3rd power, 216. Pretty damn easy. So we translate these things first. This is our big thing, is we have to know this translation, okay? And it comes into play even as things get more complicated here, even in this section. So let me jump a little bit here ahead. Anybody know this answer?
16 equals to 4 to the x.
So 2, yeah. Yeah, so this one, again, when you're looking at this first, you're like, what? Right? But when you translate it, it's easy as hell, right? Log base 4 of 16 equals x, which means 4 to the x is 16, and of course that means x is 2, right? Very easy once you translate. And eventually you'll start to think in terms of logs, right? You'll just be able to answer a log problem without having to translate in your head. Not yet. Let's look at one more and then get the hell out of here. Oh, I got some special bases I have to do. I'm sorry. So there's some special bases. Right, so 2 to the x, and our equivalent is log base 2 of x, right? When I'm writing the function in general, I don't switch the x's and y's. I'd kind of rather say f of x is 2 to the x, and my inverse is g of x is log base 2 of x. That's kind of I'd rather that notation than that one for the translation. The one for the translation is for you to be able to see that the log is the exponent, right? So, but if I have f of x is e to the x, right? Then we're saying g of x is log base e of x, but we don't write that. It's such a special number that we just write this one as ln of x, the natural log of x. And if you look at your calculator, you'll see an ln button on it, and you'll see a log button on it, right? So if f of x is 10 to the x, this is a pretty important base to us for some reason. 10 fingers. Actually, I have 9 because I gave somebody a finger on the way to work today. So here g of x would be log base 10 of x, but it's kind of silly to say that, so we just call that one log of x. So when you see those two, ln of x and log of x, know it's base e, base 10. All right, let's take a look at a problem. One or two more problems, and we're done. I only have 4 minutes. Probably not going to happen, but it's okay. This one, ln of the sixth root of e. I want to find ln of the sixth root of e. And I don't know this answer, so what should I call it? What should I call the answer? What do you think? Tony? What do you want to call the answer? X. And now I'm going to translate. How do I translate? What's my base? ln is base what?
E.
E. So e to the x equals sixth root of x of e. So e to the x equals e to the 1/6. So what does x equal?
1/6.
Yeah. Last problem. It's giving me a function and wants the domain. I have no idea what to do. Of course, I could put it in my calculator and it would be pretty easy. But what I'm going to do is translate this into an exponential, get the range, and know that's the answer for my domain of the inverse. So I've got g of x equals ln of x plus 6. Find the domain. I have no idea what to do, but I do know if I translate it into exponentials, it's easier. What's my base?
E?
E. So E, right? E is my base. What's my exponent?
X plus 6.
Nope. Remember, the answer to an ln is an exponent, right? So e to the y has got to be equal to
X plus 6.
Nice. X's and Y's are getting switched because we're doing inverse functions. So I've got now e to the x equals y plus 6. Or better yet, y is equal to e to the x minus 6. So I take my function e to the x and I move it down 6. What's my range? What's the lowest value? Negative 6 to infinity. So guess what? There's my domain. All right, a little rushed, but I knew I was running out of time. It's okay. I'll recap a little bit next time. I'll see you all Friday. Get some work done. Be good to yourselves. Get some help any way you need it.
Thank you, Professor.
No, Professor.
Thank you, Professor.
Professor, no say means I don't know.